Hello, everyone. Welcome to MIT.nano Seminar series. It is my pleasure to introduce today's speaker, Professor Jonathan Fan. Jonathan is an assistant professor of electrical engineering at Stanford University, and his research focuses on new design methodologies and materials approaches to nanophotonic systems. Jonathan has received many awards, including the Air Force Young Investigator Award, the Sloan Foundation Fellowship in Physics, the Packard Foundation Fellowship, the Presidential Early Career Award for Scientists and Engineers. And today we're going to hear from Jonathan tell us about his work on data-driven and physics-driven methods for electromagnetics design. Before I turn it to Jonathan, I just want to ask our participants to please keep the questions for the end. At the end of the talk, you can use the Q&A feature. You can either raise your hand and we'll unmute you so that you can ask your question directly, or you can also type in your question and we'll moderate. So with that, Jonathan, thank you very much for being here today, and we're very excited to hear about your work. I'll turn it over to you.
Great, thank you so much for the introduction, Farnaz, and it's really fantastic to be here and to tell you about my work. And it's particularly great to be part of the MIT.nano series because it's certainly the thesis for, I think, of a lot what I will be telling you about, which is that there have been tremendously impactful developments in microscale and nanostructure patterning of materials that has really pushed our ability to control light. And many of these developments were in fact developed at MIT. And in particular, over the last couple of decades, there have been some real breakthroughs in really new classes of optical materials ranging from photonic crystals to metamaterials and metasurfaces that are really transforming the way that we think about wavefront engineering. Tremendous progress has been made in these topics over the last couple of decades. Yet with this immense design space that is now afforded from nanostructured optical media, there exists still a number of fundamental questions with broad scientific and technological implications that still remain. These include, what are the physical limits to photonic design, and how do we design the best and most efficient photonic devices and systems? Often, at the end of the day, we want to maximize the capabilities of whatever it is that we are trying to design, whether it is an active or passive photonic device. And how do we incorporate both new functionality and physical constraints into the design process? There are, of course, many ways to think about addressing these questions. My particular focus here in this talk will be on inverse design, which is the use of numerical algorithms to search a design space through the maximization of a figure of merit. So this is, I would say, different and complementary to a lot of more conventional methods, which are based on kind of physical intuition. And as a model system throughout, I'd like to discuss our efforts in the context of metasurfaces, and in particular metagradings, which are structures that can diffract incident light to a +1 diffraction order. But I want to be clear that many of the ideas and algorithms that we are developing can generalize to many other types of photonic systems. For those who aren't familiar with metasurfaces, these are thin film optical diffractive structures that utilize subwavelength scale structuring in order to achieve diffractive optical effects and wavefront engineering. The conventional way that the field has been thinking about this over the last couple of decades has been to really take inspiration from the RF community and to consider metasurfaces as nanoscale phased arrays that utilize nano waveguides or nano resonators to essentially control the amplitude and phase response of light. Here are just some examples of variations of these conventional metasurface concepts. And it's a very powerful idea, I should just say, for many types of applications. But as we're looking to push thin film diffractive optics to new limits, including those that are very highly efficient and that are aberration corrected, as we're looking to really translate this concept to practical commercial application, it's becoming rather clear that the conventional way of thinking has certain limits. In this very simple demonstration with our metagradings that diffract light to again, the +1 diffraction order, we find actually that all of these ideas break down and result in low efficiency devices as we increase the angle of deflection. And this is also the case as we start adding aberration correction capabilities. So for the first part of my talk, I want to introduce concepts involving topology optimization, where we go beyond thinking about metasurfaces as stitched nanostructures in the form of phase arrays, and to frame this more in the context of freeform design. Now, the particular algorithm I'd like to introduce is called the adjoint variables method, which was introduced to photonics by Eli Yablonovich and Ole Sigmund in the early 2000s. And it's a really powerful freeform design concept based on gradient descent. The idea is the following. I'd like to show how this works for metasurfaces and metagradings to give you a sense of how this works. We're going to relax our design problem. And in our particular context, where we're looking to make silicon devices in air, we're going to start with a random dielectric continuum with values between air and silicon. As you can see, this is a grayscale device. We're then going to perform an iterative optimization method in which for each iteration, we're going to improve the dielectric properties at each and every voxel of the device in a manner that improves the figure of merit, which in our case is well defined and is the diffraction efficiency to the +1 diffraction order. And we're going to do this by using only 2 simulations per iteration. A forward simulation, where we shine an incident beam onto our device and we record the electric field at all the voxels in our device. And an adjoint simulation, where we send a time reversed beam from the direction of light where we are looking to propagate the field. And we will record the adjoint electric field everywhere. And it turns out, due to symmetry properties within Maxwell's equations, that the adjustment to each voxel dielectric constant that improves our figure of merit is proportional to the product of the forward and adjoint electric fields through these different simulations. And this is extremely powerful because it means that even if we have a system with potentially thousands or tens of thousands or more voxels, we only require 2 simulations per iteration in order to improve and adjust each voxel in order to improve our figure of merit. I'd like to show a video of this method at work. Here we are looking at a top view of a single unit cell of a metagrading that is being designed to diffract light to the +1 diffraction order at a 75-degree angle, which is a very difficult task to do with conventional metasurfaces. As we can see here, we are starting out with a randomized grayscale dielectric distribution with values between air and silicon. And as we go through our iterative process, we can see here that we are iteratively perturbing the dielectric constant value at each and every voxel here in a manner that improves our figure of merit, which we can see at the top. There are periodic blurs, which you can see, which is used in an attempt to kick these devices out of local optima that might be trapped in, because this is, after all, a method of local gradient descent, which I will return to later. And I should also say that there are a number of bells and whistles that we can add, such as the incorporation of robustness criteria, which is to say that our final device can be designed to be relatively insensitive to spatial erosions and dilations of this structure. This is to say they can be relatively robust to fabrication imperfections. The final device that we have here is a unit cell of a diffraction grating, which is highly non-intuitive and curvilinear. So these ideas work, and they can be used to certainly push the performance of diffractive optics and metasurfaces to new limits. Here are just some examples of structures that we've actually fabricated, designed and fabricated. These include these large angle metagratings that can diffract light with very large to very large angles with high efficiencies, multifunctional devices that can split different incident wavelengths to different diffraction orders. And in this case, high efficiency, large numeric aperture meta lenses, which again are very hard to design using conventional means. We've also done a lot of reverse engineering of these structures to understand why these structures are able to diffract light so efficiently and to perform multifunctional operation. To summarize, we have found with coupled block mode analysis that these structures utilize multiple scattering dynamics and it is a very complex light matter interaction regime that can really only be accomplished and achieved through inverse design. It's very hard to find any intuitive dynamics within these, in terms of how these work. So to summarize, the adjoint variables method and in general, local gradient-based methods are already by themselves very powerful methods to design free-form photonic structures. And for many types of problems and systems, this way of thinking is actually very much sufficient to boost the performance of technologies to certain desired limits. However, it doesn't quite address the original question which we were aiming to answer, which is what is the absolute limit that we can achieve with photonics engineering? This, after all, is really the crux of, I would say, many design problems in photonics. And the reason, again, is because this is a local optimizer. And at the end of the day, the optical design space is highly non-convex. As I mentioned already, this concept is based on a method of gradient descent, which means that it is actually highly sensitive to the initial dielectric distribution that we assume at the beginning of the optimization. And we are iteratively perturbing these structures over the course of multiple iterations. So to kind of sketch this out, what we have is we're taking devices and we're pushing them and perturbing them within our design space to find a local optimum. If our local optimum within this area of the design space turns out to be really good, then great. We were lucky with our initial condition and we can stop. However, as we can see, we're not actually searching most of the design space. And if this particular device is not satisfactory, the typical solution that we and others do with this technique is to essentially perform many local optimizations with different random starting points, hoping that one of them works. And this is an idea that ultimately works in a representative histogram of device efficiencies from random starting points for a diffraction grading. Now, what we can see here is that if we optimize 500 different devices with different initial starting points, we do find that we do have a fraction of devices that actually is quite good. This is the device that we ultimately manufacture and publish on. However, there are many devices which are actually not great. And what this means is that we are actually wasting huge amounts of computation resources by randomly sampling the design space. We're still not searching the entire design space, and it's not even clear if this device here is actually the best device. So the question is, how can we dramatically improve computational efficiency in our search for a global optimum? For the rest of this talk, I want to focus on algorithms that we have been developing in our group, where we perform data processing with deep neural networks. Obviously, machine learning has been a very popular and hot topic over the last decade in particular. I hope to convince you that this is not only an idea and interface that merits research within the photonics community, but that this actually is an extremely effective way of casting some of these inverse design problems in a manner that both allows us to improve computational efficiency and search for a global optimum. Now, usually when we talk about deep neural networks, we typically think about black boxes where we have a bunch of data and we attempt to teach a black box in order to learn from trends within this data, in order to learn some general rules. This is actually an approach that we've done some research in, and I'd like to share some of those results. In particular, it turns out that so-called generative adversarial networks can learn from images of freeform devices and generalize their geometric properties in a manner where new types of devices with related operating parameters can actually be generated from a neural network. So for those who aren't familiar with generative adversarial networks, there are actually two neural networks in one. We have here a generator, which takes random noise and which generates a distribution of devices. And what we ultimately want is a generator that, conditioned on, for example, the operating angle and wavelength of our metagrading, is able to produce devices that essentially mimic those in a training set here. We also have a discriminator that is a classifier that has an input that is either a device from the training set or a device from the generator. And it attempts to discriminate whether the device that is inputted into the discriminator is from the training data set or the generator. Now, of course, a generative adversarial network doesn't know how to generate good devices or discriminate between generated devices or those in the training set. But it turns out, and this is something that was developed in the machine vision community, that if you pit these two neural networks against each other, you can actually train a generator to essentially mimic and learn the distribution of data within a training data set and to ultimately mimic and interpolate within this data. So in our first generation GAN, we essentially use kind of this off-the-shelf type of architecture to basically train a generator to learn from images of freeform devices. That's more details can be found in this paper down here. In our second generation GAN, we actually created a new type of training methodology where we started with a sparse training set. This is to say images of freeform devices that span, that have a kind of select wavelength and deflection angle values within our parameter space. And we go through a set of training cycles where in each cycle, we basically train a generative adversarial network using so-called a progressively growing network. We generate devices, we generate devices here. We actually evaluate and filter out for high efficiency and robust devices. And then we augment the training set and then we repeat the cycle multiple times. What we get at the end is a generator that can basically mimic and understand how to produce images that represent high efficiency and robust metagradings spanning this continuum of wavelength and deflection angle values. So this is what we get with our trained progressive growing GAN. We have a network that can produce a wide variety of freeform images of freeform devices that are both highly efficient and also robust. I should emphasize that this idea of robustness, which is to say that a structure has high performance both with its device layout, but also its physically eroded and dilated layout, is a very subtle physical constraint to be had within a design space. But through proper training methods, progressive growing GANs can actually learn these type of criteria. So to summarize this part, the key takeaway here is that with the proper way of training, neural networks can actually learn and highly intricate trends within a training data set, and in particular, within even data sets as complex as images of freeform devices. They can actually learn and generalize geometric features from these type of images. So they certainly have the capacity to do a great amount of work. However, what is this general paradigm, I would say, of learning from data sets of devices, while very effective in, for example, filling out a library of different classes of devices, in this case, operating across a range of wavelengths and angles, still doesn't address the question of whether or not we can utilize these networks to perform global optimization. So for the rest of my talk, I'd like to introduce another new algorithm that we have been working on, where we actually are looking to reframe the training of a neural network um, as an optimization process itself. So just recall with the adjoint variables method that what we are doing is we're taking a physical device. We are performing physics-based simulations to find gradients to essentially iteratively improve and perturb this device. What we are going to do now is we're going to replace this device with a generative neural network. And as I will show you, this actually allows us to do a population-based global search within the design space to very efficiently find the global optimum. What we have here, again, with our generative network is a neural network that has an input of random noise. This random noise can be sampled to produce a distribution of devices. This is to say we are indeed doing population-based optimization. And instead of working with any type of data, a training data set, what we're going to do is we're going to train this generator to produce over the course of many iterations devices. We're then going to evaluate those devices with an electromagnetic solver and use that information to backpropagate and improve the mapping of random noise to improved devices, with the idea that over the course of this entire network training process, random noise will ultimately map onto a narrow distribution of devices that are actually at the global optimum. I'd like to go through this theory just a little more, at least schematically. As I was saying early, the design space for photonic devices is highly non-convex. That means if we take all devices, and this of course is an absolutely massive space, we'll find that there are many local optima or saddle points, and that it can actually be quite hard to randomly find the global optima, which is represented here, and we're going to represent this globally optimized device as X star. The way that we're going about this is very different from, I think, the way you typically think about design and optimization, where in the case of the adjoint variables method or genetic algorithms or anything you might be used to, you are focused on designing within the physical space, right? You have a physical device that you perturb in order to make it better. Here, we're going about this in an indirect way. We're starting with a generator that maps noise onto devices. And instead of optimizing the devices and their layouts themselves, we're actually going to optimize weights of our generative neural network. And in particular, we want to find weights that give us this optimal output distribution. Here, what we have is a very narrow distribution centered around X star. And we can have these type of highly narrow distributions because these generative networks are extremely nonlinear algorithms. So with this in mind, we can cast our optimization problem where we want to find weights of our network that maximizes the following. Here, this delta function of our outputted efficiency minus our globally optimized efficiency is non-zero only if our outputted devices are globally optimized and have efficiencies matching this. And this is our distribution of outputted devices, which we want to have to be as narrow and peaked around X star as possible. If we use this as our starting point, we can then go and engineer a loss function that attempts to achieve this optimization goal. And I'll skip through the math and just tell you what this loss function is. And it is the following. We have a term that has, of course, a batch size. This is to say we will be sampling our generative neural network and to create a batch of devices each and every training iteration. We're going to weigh this loss function by a term that is proportional to the e to the efficiency, which is to say that the higher an efficiency a device has that is being generated, the greater it is being weighed. And we will also have here a gradient term, which actually represents how a device efficiency can be improved by changing its by changing its voxels. And this is exactly the same gradient, local gradient that is used in the adjoint variables method. So to summarize this part, in order to train our neural network, we're going to be generating batches of devices, evaluating its efficiency and efficiency gradients, and then back propagating these back into the network using this engineered loss function in order to improve this mapping towards our optimization goal. Okay, so does this actually work? Well, I'd like to show you the results, firstly, of locally optimized devices based on the adjoint variables method. Here, what we've done for each angle and wavelength is we've optimized an ensemble of devices that is, as we've seen before, we have many devices that are not great, but we have some that are very good. And here we have the best out of 500 locally optimized devices. Here, what we've done is we've trained a single generative network. We're calling these global topology optimization networks, or GLONets. And we can see that for some cases, this works better. The best GLONet device is actually better than the best of 500 locally optimized devices. Here, it's actually a lot better. This is to say that it turns out that there's some areas of photonic design spaces where it's just very hard to brute force find really good devices, even with lots of local optimization attempts. It's not perfect. Here, at the end, this is a statistical method, and here the best GLONet device doesn't work as well as the adjoint variables-based device. But in general, this method, as we have benchmarked this in very quantitative ways, in general, is both significantly better than the local optimization method, and it's also much more computationally efficient, because instead of spending a lot of time doing entire local optimizations in regions of the design space that are not great, it does ultimately search and shift the mapping of noise to devices to parts of the design space that are more promising. Okay, I'd like to show in a little more of a visual way how the GLONets training algorithm works. Here we are looking to train a GLONets to basically find a metagrading that operates with this particular angle and wavelength. And of course, your network doesn't know anything about what a good device looks like. So, in sampling this network at the get-go, it produces devices that are mostly extremely poor. As we go through our training process, what we find is that the distribution of devices over the course of training in general gets better. And as we can see, is getting more and more peaked towards higher values. Here we are visualizing the design space, where initially we were searching the entire design space. And over the course of training, the network actually collapses onto this very specific part of the design space that produces really high efficiency devices. So this network is doing exactly what we want it to do. It is now outputting a very narrow distribution of devices. In fact, many of the same devices that are extremely efficient. To show the stability of the network for this particular example, we can see here that when we train 8 of these networks from scratch with different initialization values, we find that 6 of the times we get the exact same device. In this particular case, a device that works with 97% efficiency. And while we cannot prove that this is the global optimum, it is interesting to see that these networks can in fact converge to the same type of devices. And furthermore, that we are now in a new type of operation regime for metasurfaces. I mean, devices that operate with near unity efficiency is not a concept that is typically associated with the metasurface field, but with these very unusual and non-intuitive unit cells, it is actually possible to really push the performance limits of metasurfaces towards those of other types of optics, close to those with anti-reflection coatings, which is very exciting. So for us, we were indeed very excited to get these results. We took these designs and we tried to go into the clean room, of course, pre-COVID, to make these. And we just couldn't make these, in part because these devices were very sensitive to fabrication imperfections. This particular gap is on the order of 30 nanometers. It was just very hard to make these type of devices. Which indicated to us that it was not sufficient just to globally optimize devices, but that we had to be able to understand how to globally optimize devices within a design space with physical constraints. And this has led us to a way of thinking about enforcing constraints that is actually very general and very powerful, and certainly amenable to our GLOnets platform. So this concept, which we term a reparameterization, involves the design of devices not in a physical space. Usually when you think about constraints, you think about, again, designing in a physical space and for example, penalizing devices that might be violating certain constraints, but they're not hard constraints. What we're going to do is we're actually going to design devices in an unconstrained latent space. So this is to say that devices in this unconstrained latent space can take literally any real value, and but their exact representation in these latent spaces is not physical. We're then going to use a set of analytical and differentiable mathematical transformations in order to map devices in this unconstrained latent space to those in this constrained device space. And through this process, if we properly choose these type of analytic mappings, we are able to essentially map all of these devices in a very robust way to a subset of our design space that satisfies our constraint criteria. So this actually does two things. I just want to be clear. The first is that it ensures that it's not even possible to have devices that are unfeasible or that violate our design constraints to be even considered. The second is that it reduces, in fact, dramatically, the size of our design space. Instead of considering all devices and needing to come up with methods to attempt to eliminate some of these devices, we already are constraining and reducing our design space already, which makes its global search that much more effective. Okay, to give some more details on how exactly this works, I'd like to maybe first talk about this in the context of local optimization before I get to the GLOnets variant, where what we have, again, with local optimization in a conventional sense involves taking a physical device and then using the adjoint variables method to find gradients that improve this device. What we're going to do now is we're actually going to add these additional parts to our computation graph, where we are actually optimizing in this latent vector space. This is unconstrained. Each of these numbers can take any real value. We're then going to mathematically transform these into a width vector space to give us physical devices that have constraints. And then we're going to take these width vectors and we're going to do a second analytic transformation to convert these into a blurred pixelated pattern, which we can then evaluate with the adjoint variables method. Improvements to devices based on these gradients can then propagate all the way back to improvements to the latent vector representation using the chain rule, because all of these different parts are connected through analytic and differentiable expressions, and therefore this entire computation graph can be auto-differentiated. Now, there's some leeway as to how exactly we incorporate these constraints. Here, I'd like to show something that we did, which actually turns out to work quite well, which is that in translating our width vectors to our grayscale dielectric structures, we actually model these forms, these dielectric distributions using the Fermi-Dirac function. And this is useful because, as we know, with the Fermi-Dirac function, at high temperatures, we actually have something that appears a grayscale, right? We have a temperature. This actually allows gradients to propagate properly throughout this entire computation graph, and allows the optimization to work out quite well. And what we can do is we can manually lower the temperature to 0 over the course of optimization, at which point, when t is equal to 0, the final structure is binary, and we have something that is all silicon or air. So let's go ahead and see how this actually looks. We are starting here with a random grayscale structure that has a temperature. This is to say we can see in this pattern profile that this is indeed grayscale. The initial efficiency is poor. And as we go through this local reparameterized optimization, we can see we are dropping the temperature, the efficiency is going up, and the final device is indeed binary, and it has a high efficiency. So this is the essence of the reparameterization concept. Now, as we move to reparameterization with GLONets, it becomes clear how we do this. We have a generative neural network that outputs not physical devices, but devices that are in a latent vector representation. We use our analytic mathematical transformations to transform these latent vector representations to physical grayscale devices, which we can then evaluate with electromagnetic solvers. Finally, to improve the mapping of noise to devices, we use backpropagation, and we can backpropagate these physical gradients all the way back to the neural network weights in our generator, because again, this entire computation graph is differentiable. Here are some results where we can see that as a function of minimum feature size, we get when we have no, really no minimum feature size constraints, that our best device is 97% efficient, and it consists of 3 bars. This is exactly the device that I showed a few slides ago. But as we go to larger and larger minimum feature sizes, there is, of course, this trade-off between feature size and efficiency. And we actually find that entirely different devices with different topologies become the globally optimized ones. Here we can see in this GLONets that can actually optimize for different topologies, that we can get with a network these different types of devices with different topologies that are globally optimized. Here we can see as we go to different minimum feature sizes that we actually get devices that look completely different. Okay, in the last few minutes that I have, I'd like to show how these ideas can adapt to other types of problems in photonics beyond just diffractive optics. And I'd like to show in particular this problem, which I think you're all familiar of from classes, which involves optimizing thin film stacks. And I would have thought myself, until I looked at this problem, that thin film stack design is actually a solved problem. It's been well defined for over half a century. But in fact, it's a pretty complicated combinatorial problem for which GLONets is ideally suited for. In this particular problem, it's a bit different from what I showed before, because we are not only looking to optimize film thicknesses in a continuous way, but we're looking to select from materials, and in particular from a library of discrete materials, which actually adds a little wrinkle to this problem. So this is what we're doing. We have here our generator that generates different types of devices. Here we have thickness and refractive index for different layers in our device. We use a transfer matrix method solver, which can be written in Python in an analytic fashion to evaluate our reflection spectra. And then we have our loss function, which evaluates how close those devices are to producing the reflection spectra we desire. And we backpropagate this back to the generator to improve the mapping of noise to useful devices. Now, one of the challenges here is we are dealing ultimately with a library of discrete materials. And as we know, whenever we have discrete variables, it can be very hard to backpropagate gradients in that case. And we therefore have to relax these discrete math problems into continuous variable problems. And to do that, we're using some tricks from image classification and categorical optimization, where our generator is not generating discrete refractive index profiles, but it's actually generating a matrix here with a continuum of values that can be transformed using the softmax function into a probability matrix. The probability matrix tells you for this particular row the probability that this particular layer consists of the, in this case, the M1 material, in this case, the M2 material, et cetera, et cetera. We can then take the expected value of the dielectric constants at each layer with this probability matrix using this expression here, which we then use as our refractive index profile for evaluation. This entire probability matrix concept is differentiable and something that is amenable to the backpropagation process. And furthermore, with the softmax function, which is equivalent to a partition function in physics, what we find is that as we manually adjust alpha in a manner similar to our temperature term from before, we can essentially force the probability matrix to converge and take on nearly discrete values in terms of dielectric constant. One other thing I want to mention here that we realized is that if we incorporate a residual network for our generator, we can actually improve the overall mapping of our of noise to devices over the course of optimization. Residual networks, for those who are not familiar, involve neural networks that not only incorporate a block of neural network layers, they also incorporate this shortcut function that can actually so-called simplify these very deep networks. This is a concept that has been used for a number of years in very deep image-based networks. The idea is the following. We want to find this global optimum in this really complicated objective function space. During the middle parts and intermediate parts of our training process, what we're trying to do is we're trying to get our generator to actually map out and mimic some of the complex and non-trivial curves within this objective function. That means that this network does indeed need to be very deep and have enough degrees of freedom to capture this nuanced landscape. But our final ResNet is attempting to collapse onto this global optimum. And it turns out that the shortcuts here can actually really help create a mapping function from noise to devices that is much more simplified and much more emblematic of our desired final probability distribution. Okay, so let's see a couple of results. The first that I'd like to show is an anti-reflection coding. We chose this specifically because there's a really nice study from right here from MIT by from Mark Baldo and Steve Johnson's group, where they actually did a brute force search for the global optimum for anti-reflection coatings for solar cells. I believe that took a number of days, but the main thing is they actually had a hard a global optimum for these thin film stacks that we could benchmark against. For us, we were able to use our GLOnet. We were actually able, here as we can see in this histogram, we were able to find the same global optimum as found in this paper, and we were able to do this in 7 seconds. So this is indeed a method that, at least with this one example, was able to find the global optimum. This can also apply to more complex problems where the solutions are still open-ended. This is a very interesting idea that was actually proposed by Marin Soljic, where what we want to do is we want to improve the efficiency of an incandescent light bulb by creating thin film filters that transmit visible light and that reflect UV and thermal radiation so that it can basically be recycled to keep reheating this thermal emitter. This is a pretty complicated multi-objective combinatorial problem. With a library of 6 materials, this is what we find. We're actually able to get a 45-layer device that maps this desired profile quite well. And if we compare this to some existing benchmarks, we actually find that our algorithm works better than others, which actually use a combination of machine learning, global optimization, and local optimization. And this improvement may not seem like a lot looking at the vertical scale, but if we trace along the horizontal scale, what that means is compared to this mimetic algorithm, for example, we're able to get the same performance with half the number of layers. Okay, so where do we go from here? I'd like to just say a couple of words. The first is hopefully some of you are convinced that metasurfaces, where we have relatively thin device thicknesses and high contrast, is an interesting and new regime for diffractive optics. What hasn't really been explored is this arena nearly as much until very recently. Ones where we have thick devices and high contrast media. These are exclusively multiple scattering media, in essence, that require inverse design to fully exploit. And with a huge number of degrees of freedom, there's a great opportunity. Here's some preliminary work that we've done showing that as we do go to multiple layers, theoretically, we can truly create flat optics that can support really extraordinary capabilities. A number of groups, including those from Steve Johnson and Andre Farion, have shown some very great theoretical and experimental work in this vein as well, and I think it will be a major thrust for photonics engineering. The second thing I want to say is I think it would be great for us as a community to coordinate research efforts, especially in this burgeoning field of algorithm design with neural networks. If we look at machine learning in the CS community, that research is largely driven through open source coding and proper benchmarking of algorithms that have really enabled the field to just blow up. And our field is not good at sharing data, sharing codes, and benchmarking with common training criteria. I think as a field, we need to do more of that. My group has attempted to put what is essentially like an archive for people to upload codes and images where we have some users, but I think culturally we need to shift things a bit. So to summarize, deep learning is the foundation for the next generation of CAD-based inverse design tools. Not because neural networks are a flashy area of research, but because neural networks are able to learn non-intuitive data transformations between inputs and outputs in ways that are truly new. And furthermore, I should just say that as we project over the next 5 to 10 years, there's going to be so much additional advancement in both the hardware and software for neural networks that researching in this direction will reap the benefits of everything that is happening in the CS community, as well as in new hardware development for machine learning. The key is not to focus on black boxes, but to, as physicists ourselves, really think about hybrid algorithms that combine physics and physical constraints with these black boxes to create something that is entirely new. There's clearly more innovations required to scale up these concepts to large area 3D systems. I think there are pathways there. Just to give one example, it's going to become absolutely essential to have really fast electromagnetic solvers. But it turns out that the data sciences may hold the key to that too. Steve Johnson recently put out an archive paper showing how active learning can be used to make application-specific solvers that are extremely fast and accurate. This is just a really burgeoning field that's going to really be, I believe, taking off. Finally, I'd like to thank my research group and funding agency. A lot of this work has built off of many years of effort and lots of people. And very lastly, for those of you who think this is interesting, who are perhaps new to machine learning, and want to understand more about its connections with the physical sciences, I want to point you to this review article that is about to come out in Nature Materials Reviews that is on archive. Thank you very much for your time.
Thank you, John. Thanks for a great talk. We have a few minutes for questions. So if you have questions, please either raise your hand and we can unmute you so that you can ask your question directly, or you can type your question in the Q&A section. Ali is asking, what are real-world application of reparameterization, industry or business cases?
Yeah, let me back up and say this whole concept of reparameterization is a very general concept, and it's actually used rather commonly in the CS community in order to incorporate constraints into data science problems. In the context of a lot of these physics problems, I think this concept of reparameterization really can be framed to capture almost any physical constraint. And what I showed in this example, we're looking to incorporate a minimum feature size constraint. But you can imagine using this for many other problems. Just to give you an idea of something that my group is working on, if you want to create a multi-layer metasurface and you want to ensure that the structure on the top doesn't have an overhang, on one hand, you can try to manually incorporate that type of constraint and to attempt to use penalty terms to prevent that from happening. Or you can think about using reparameterization as a means to ensuring that your design space doesn't even have structures that have overhangs. There's also a really nice paper actually from MIT in the design of microwave circuits, where they used reparameterization just to ensure that in considering a design space of coupled resonators, that the coupled resonators didn't overlap and were constrained physically in certain configurations. So to kind of summarize, I think this idea of reparameterization actually is extremely general. And pertains to the incorporation of any type of physical constraint that can be described by an analytic mathematical expression.
Great. So another question we have is, if our goal is to find the best solution, why do you output a distribution?
That's a great question. At the end, we utilize the distribution throughout the entire design process to ensure that we do population-based optimization and a population-based search within the entire design space. You really have to be able to search the full design space and have different parts of the design space basically talk to each other so that you can kind of push your desired outputted distribution towards more promising regions of the design space, which is actually what happens. So at the end of the day, just to be clear, your network is indeed still producing a distribution of devices, but ideally it's narrowly distributed in a way where you don't have to sample the generative network nearly as much in order to find a really good device. And the second thing I will say is that it really gives you a lot of flexibility to really shape the type of distribution that is outputted from your network. Sometimes, if you're really confident, you really want the network to collapse. But if you have a really complicated design space, or perhaps if you want to find many good local optima instead of just a single good global optimum, you want the outputted distribution to be different. So this is to say, I think this is actually a very interesting degree of freedom where through loss function engineering, you can really mold and tailor the outputted device distribution to take on one of a number of characteristics you might desire.
Wonderful. So could you comment on the physical origins of the thin film stack design improvements through machine learning, especially compared to conventional quarter wave structures?
Yeah, great question. Our choice of the two examples that I showed, the anti-reflection coating and this infrared um, and this basically this incandescent light bulb filter, I think were specifically chosen because uh, there aren't really simple analogs to kind of thin film stacks to really improve to capture this type of performance, right? Thin film stacks could be used to say to be reflective for a range of wavelengths, but not to transmit a range of wavelengths and then to reflect all the other wavelengths. Um, so, uh, so yeah, for kind of the idea behind these particular structures is kind of the need to create what are ultimately very aperiodic, uh, thin film stacks that utilize interference in entirely non-intuitive and crazy ways in order to achieve what I showed you. And I should say this should not take away from uh, any application where simple design methods work. In fact, you clearly should use simple design methods if, for example, uh, periodic thin film stacks are sufficient for your application. But in the case where you want to really reduce the number of stacks, in the case where you just have to use really bizarre and complicated interference phenomena, this is the way to go.
Great, so we have a few more questions. So the global net and neural networks in general require a large amount of data in order to successfully train. In the photonic space, this is in particular a problem since individual simulations can take minutes or even hours. How do you propose moving the neural networks to larger design problems, perhaps 3D structures?
Absolutely, we're working on that. I think the key will be figuring out how to innovate faster solvers. I remember talking to Steve Johnson about this a number of months ago, pre-COVID, where I think kind of generic electromagnetic solvers as we know them, right? FDTD, FDFD, FEM, RCWA. Uh, Generic solvers are near their limits of, order of magnitude limits of how fast they can go. And I think that's where, there still need to be breakthroughs in just getting much faster solvers that could allow these optimization methods to scale to uh, problems of much higher dimensionality. But I'll cite two examples of where I've seen this, which indicate, I think, the hope of this actually being able to go beyond model 1D systems. The first is, as I was mentioning before, work by Stephen Johnson, where through active learning, he is able to train a neural network, a discriminative neural network, to basically serve as a high-speed solver. And the entire evaluation and training of this network reduced the overall computation overhead by an order of magnitude. And the second is work by my colleague, Jan Vukovic, who's actually using a convolutional neural network to basically create application-specific FDFD solvers that can essentially perform, that can effectively serve as a data-driven preconditioner to accelerate those type of electromagnetic solvers. So I think there's a tremendous opportunity that's really untapped at this stage to understand how to accelerate EM solvers, not just by a little, but potentially by orders of magnitude. And I think that will open up the door not only to really take these type of data and physics-driven methods to the next level, but really for everyone's research. I mean, I still remember time as a grad student just sitting in front of my computer waiting for a simulation to end. That should not happen in the future, in my opinion.
Great, so the next question is asking, have these devices generated by the neural nets guided new intuitions or insight for the physics and geometry of the devices?
Yeah, that was certainly the goal for applying inverse design for some of these diffractive optical structures. And we spent a lot of time reverse engineering those structures using these coupled block mode analyses to really understand the modes, kind of the multiple scattering dynamics, to see if there was anything that could be generalized, to the point where we would even have just two ridges coupled together, almost like, two artificial atoms just coupled together. And it would be amazing to see, even in a system as simple as two coupled ridges, how non-intuitive and non-generalizable those ideas were. So I think this is both, both a blessing and a curse, I would say. It was, of course, part of my goal to attempt to find really new physical insight that could, generalize, some of these concepts in design in a way that's much more tractable, right? And digestible in a way that we as physicists and engineers prefer to think about problems. But I've been doing this long enough to understand that, at least for these types of problems that I'm showing, that type of intuition does not seem to exist. And I guess that is also the opportunity for thinking about these more as straight up optimization problems, with an understanding that there is just a great deal of non-intuitive thinking and dynamics that goes into maximizing performance, and that for many problems, it's just not that elegant.
So this is a question from a machine learning person, as is written here. So it says, interpolation within a large number of data points can be done well through any number of function approximation schemes. How well are these networks extrapolating away from the data?
Yeah, so in the case of the GANs, which I showed in the middle part, it certainly has proven to be a very good interpolation tool. But for those who are familiar with how these networks work, right? You're mostly fitting the form of your training data. So from an extrapolation point, it's not great, and that's where, sampling in our case, this angle wavelength space of devices kind of uniformly and interpolating within them has proven to be the most effective means of generating training data in order to use training data to train a GAN. The GLOnets are different, right? Because initially, what the GLOnets is doing is, if it is ideally initialized, random noise is actually being mapped onto the entire design space. So you don't make any assumptions. There is no training data, and you don't make any assumptions about what is what in the training space. What you then do is you kind of sample this space and gradually push this mapping function, towards more promising spaces until, ideally it does focus and collapse onto the global optimum. So this is just a different way of using generative networks that at least I've seen in the machine learning community. I'm not a machine learning researcher formally, though. In fact, I'm an experimentalist waiting for COVID to end. but my understanding, talking to my colleagues in optimization and machine learning, is that these type of methods are often not very closely studied in machine learning, and part of the reason is because it's very unusual and rare to have such physical such equations to describe, your design space and local gradients and things like that. I mean, if you're categorizing dogs and cats, there's no function that tells you, oh, this funny cat can be made better by putting it in this analytic function. But in photonics, it turns out that, these functions exist. So I think this is where there's some very interesting opportunities. We have physics, we have physical equations, we have a lot of analytic tools and quantitative tools at our disposal, and that's where we're looking to design entirely new hybrid algorithms.
Wonderful. A couple of more questions.
Sure.
Does any of your research involve graphene or nanoporous silicon surface applications? And
So, oh, graphene, you said?
a comment that says we're focused on life sciences and your neural network deep learning techniques on such metasurfaces seem exciting.
Yeah, I think this is something that can be tailored to many different systems. And I just want to emphasize, I don't think this is something limited to nanophotonics. So we haven't quite worked on those very specific topics, though part of my research groups actually works in nanomaterials, and I think it's something that we can definitely look at down the road. But I just want to emphasize, I mean, I think we have used nanophotonics as like a really nice model system. But thinking about the very wide range of so-called metamaterials and acoustics and mechanics, I think this will be very interesting. I think, you know, in circuits, thinking about even materials discovery, there's a lot of, you know, really exciting work in fluid mechanics and that whole community with solving differential equations with neural networks. So yeah, it's extremely broad, and it doesn't mean to say that the exact algorithms that I'm showing you today are going to apply to, you know, it just very directly in all these different problems. But I think there are just huge opportunities across the board in the physical sciences, and that it really takes people from our fields, whether it's, you know, biology or material science or electrical engineering, to learn and use these things. There are too many data scientists out there, but there are actually very few data scientists who have very deep physical physical sciences backgrounds. And yeah, there's a huge opportunity.
Wonderful. Last two quick questions. Yeah. Is the GAN to the, how specific is the GAN to the optimal photonics design we're trying to achieve, for example, between the stack or the metasurfaces?
Yeah, I think the GAN is something where, especially with this whole cycle GAN that we've developed as our second generation GAN, the final devices are as good and sometimes a little better than the best globally optimized devices from local optimization. So it's a great way, if you have really good devices in your training set, to basically get to up to that point. Again, for many problems, I mean, this is sufficient. You don't have to find the global optimum for all problems. It happens to be a great way to learn from sparse data and to kind of generalize these design concepts. But it won't, again, it's good at interpolation, and therefore it won't just find and extrapolate and find the global optimum if your global optimum is not already in the training data.
Okay, and the last question asked, is the symmetry imposed?
Yes, we incorporate kind of XY symmetry depending on whether we want our metasurfaces to be polarization dependent or polarization independent. But you can imagine there are many games you can play with incorporating symmetry into neural networks. Certainly, I think there's a whole slew of symmetries, especially as you go into other topics like topological photonics or others where you can certainly incorporate unique symmetry properties. So, but it's something that we incorporated it as convenient for us, but we didn't. But yeah, it's something that can be exploited even more.
Great. Those were all the questions. Thank you, John, again for the great talk. And thank you all for attending our very first seminar series for this year. The next one will be next month, and you'll receive more information shortly from MIT Nano about it. Thank you all.
Great, thank you.